I just wanted to mark this occasion, the sad passing of Val, A.P. Balachandran, who would normally be here to hear Howie's talk. Was just he was a regular participant, and we just wanted to mark the occasion.
Okay, thank you.
Thank you so much, Nigel. Yeah, so it is indeed very sad. Well, yeah, not very sad note. It is my absolute honor to introduce today's speaker to you. Howie doesn't need an introduction. He is my self-appointed godfather, but he is well known for his work on Higgs physics and scalar extensions, especially two doubler models. You've all seen the Higgs Hunter's Guide, and I always joke that the 2H in 2HDM stands for Howie Haber. Howie has been here visiting for about a week now, and then we're off to Corfu for a future accelerators workshop. But before he goes away, I thought we'd get a seminar out of him. So he's going to talk to us about a recent paper he's done with another one of our wonderful collaborators who actually was a DICE member, Pedro, a bunch of years ago. I don't exactly know where. I'm going to give the floor to Howie to talk about field theory in scalar extension.
Yeah, thank you, Ring. So it's a real pleasure to be here for my second time. And what I wanted to tell you about is a curious problem that arose. We all have expectations about how we understand quantum field theory and various facets thereof. And there are certain things that you think are true for many years, and then one day you see a talk and there seems to be a result that appears to be very counterintuitive and perhaps in violation of some of your expectations. So when this happens, you take notice. And so I'm going to give you a little story about how this happened and what our resolution was. And this is a paper that we released in February, and it's about to come out in that publication as soon as they send us the proofs. Okay, I guess I have to closer. This worked just before. All right, that's unfortunate.
If you hit the space bar, it probably goes to the next page.
Boy, you know, I wonder if this is a problem with being connected to Zoom. Somehow it's not responding.
It's not on the page if you're trying to.
Sorry? No, nothing is working. Oh, there. Okay, now, okay. All right.
It was just busy.
It was just busy, yes. So the outline of the talk is, I'll start with what I expected to be true that seems not to be totally general. I'll give you some background, how this problem arose. And it basically started with some other researchers looking into possible symmetries of the Higgs double model and certain parameter relations, which apparently seemed to come out of nowhere. And what was remarkable was that these parameter relations seem to be completely stable under a renormalization group evolution, which usually associate with the existence of symmetry. And so I'll tell you the story and how we attempted to solve it. So, in some sense, it all starts out with what I thought was a theorem. So in quantum field theory, which you write down, kinetic term, potential terms, etc. there can be relations among the parameters. But if you just take random relations, they're certainly not going to be stable when you run the renormalization group, change the scale. And if it's not stable, then it's kind of a total fine tuning about choosing that particular relation. So in realistic models, you would prefer, if for some reason you want certain relations to hold, for it to be stable. And if there's a symmetry lurking behind, that could explain why a particular relation actually is stable, which means that there are some beta functions in the theory and they're fixed points. And in fact, if that symmetry is softly broken, you still maintain the RG stability, although the parameter relations at tree level can be modified radiatively, but those radiative corrections will be finite. If you didn't have the symmetry, then they would be infinite, then you would have to introduce counter terms. That's where the fine tuning arises. And okay, that anyone who's worked on quantum field theory knows quite well. But what I want to suggest to you is that I've always assumed, or lots of people have always assumed, that the converse of these statements was also true. In other words, that if you just happen to notice the renormalization group stable parameter relation, there must be a symmetry underlying to give you an understanding for where that fixed point in the beta function came from. So there was this paper that was released in 2023, published the following year, by my co-author, who I stole from this paper to follow up. And they were studying the 2x doublet model. And they discovered a particular parameter relation that surprisingly was completely stable under a normalization group running, and yet did not appear to be a consequence of a symmetry. And so they struggled with this, and they decided that they could construct the symmetry, but the symmetry they constructed was incredibly bizarre. I'll try to explain to you why I don't think what they called a symmetry was really symmetry. I think it was really illegitimate. And so that's what started this whole work. Okay, so let me give you a background on the 2x doublet model and possible symmetries. And I'm only going to consider the bosonic sector, so I'm going to throw away the fermions, although in the paper by Ferrer et al., the fermions were included, and when you worked out the beta functions, they included the effects of the Akawa couplings. But let's just focus on the scalars in the theory. So I have two Higgs doublets, phi1 and phi2. There's a kinetic energy term, which I see I have a nice little typo there. Obviously, this thing should be dropped. This thing is equal to this. Apologize for that. And the potential, here's the most general renormalizable gauge invariant potential you could write. It's complicated. It's 3 squared mass terms, 7 quartic coupling terms. Some of these couplings are real by hermeticity. Some of them are potentially complex. And if you're a model builder and you want to study, for instance, the phenomenology of a model like this is too many parameters. In fact, this model generically has 11 independent parameters. And that's not even including the Akawa set.
And you've written covariant derivatives, so you are going to take the gauge fields into account?
Well, yes, the gauge fields are taken into account here. In my toy models, I will not have gauge fields, but in the initial, in the paper that was studied by Ferrer et al., it was the full 2x doublet.
Where's the 11th parameter? I can see that.
Well, there are actually 14 if you count the 4 complex parameters and then the rest are real, you would get 14. But then I can.
Oh, yes.
But then I can start to do field redefinitions. At the end of the day, only 11 of them are physical, but still too many. And so what people tend to do is they try to make models where they impose symmetries. And then one of the questions that arises is, can you classify all possible symmetries that you can impose? And the remarkable thing, so let me tell you what types of symmetries we're thinking about. One is sometimes called Higgs flavor symmetries. This is just a rotation, well, a unitary rotation. This S matrix would be an element of some subgroup of U2. You could also have what's called generalized CP symmetries, which in addition to this unitary transformation, you take the complex conjugate. So these are 2 different classes of symmetries. And after a lot of work, which is, you can see in these papers here, all possible inequivalent symmetries were classified. Now, the meaning of the word inequivalent is a little bit subtle because, just as an example, if I were to take this S to be a Z3 symmetry, I would discover that the parameter relations that it imposes are exactly the same as if I had chosen U1, full U1, in which Z3 sits in. And part of the reason for that is because we're talking about symmetries of a renormalizable Lagrangian, so it only goes up to quarter. So that's really what I mean by inequivalent. So here's the complete list, only 6. I could have a Z2 symmetry. I'm telling you what the transformation laws are for, say, the first and second Higgs doublet. For U1, this is sometimes called U1 Peche-Quinn. This is basically the full U2 symmetry, but U1 hypercharge doesn't do anything to the parameters. This is an SU2 cross U1 hypercharge invariant theory. So the relevant symmetry here is U2 sort of modded out by the U1Y. And then the generalized CP symmetries, this is the one everyone knows. You just star the fields, but you can also do some other interesting things. And there were 3 classes of those. And notice here that theta is a completely arbitrary parameter between 0 and half pi, but for any choice of theta, you get the same parameter restrictions. And so now I could take these 6 and make a little table and tell you what it does to those parameters that I had before. And here it is. So, for instance, this particular symmetry was GCP2 sets M11 squared equal to M22 squared, sets lambda 1 equal lambda 2, sets lambda 7 equal minus lambda 6. And the blank spaces means it doesn't constrain it. And so there's the complete list. And one thing you might wonder about is, what about other possible symmetries? Here are just 3. I've given them different names. For instance, this pi2 interchanges phi1 and phi2. I'll show you a table that looks like this, and the parameter relations will look different. And so why do I say that this is the complete classification? So here are a bunch of other symmetries, and here they look different. And the reason is because it turns out that any of these symmetries, you can find, this is called a change in the scalar field basis. This is just relabeling the phi by unitary transformation. You can find a U that sort of turns these relations into one of the 6. And one thing that surprised me that we discovered in this paper is that there was something that we call GCP1 prime. And if you look at this, it has complex parameters. Lambda 6 is complex, M12 squared is complex. But it turns out that it is secretly just the standard CP transformation that basically sets all the parameters real. It just happens in another basis. So that was kind of curious. But okay, so we know what's possible. And so now let's look at renormalization group equations. Here I've written out a one loop only, although there are expressions that go 2 loops and even 3 loops in the literature of how the beta functions of all the parameters. They look complicated, but now let's do a little example. Here's that GCP2 symmetry, which imposed these 4 relations among the parameters. And you take those renormalization group equations, and you can check that all of these have fixed points at this particular choice of the parameters. So this is what I mean about saying that the renormalization group is stable. So I put this SYM notation to tell you that when you evaluate this particular quantity, you stick in the values corresponding to the parameter.
Can you show us the beta function equations again? Just
Yeah.
one time, they would like to quickly.
I mean, there's a little bit of algebra involved, but you just do this subtraction.
Oh, yeah, I can see you presumably done a dimensional regularization and just said so it worked at 4 dimensions.
Oh, you mean how these were calculated?
Yeah, I'm just
Yeah, the standard methods.
Sorry, could I have another look at the GCP1 prime?
Well, that's part of that was just a throwaway remark.
Okay.
It's just to let you know that if you see a parameter relation, it's not obvious and it's not one of the 6 that you know. You still have to do a little work to make sure it's not one of the 6 in a different basis. Okay, so well, this with those one loop beta functions, this is a pretty simple algebra to verify, but you can do 2 loops, you still get 0, 3 loops, you still get 0. That's what quantum field theory teaches you. You've got a symmetry, and therefore it's a fixed point. And in fact, even though I've just shown you the beta functions with the scalar self-interactions, there are additional terms in the 2-Extella model that involve the gauge couplings, involves Yukawa couplings, and you can put that all in and it doesn't change. I mean, it's a symmetry as long, well, if you put in the Yukawa couplings, then you have to make sure that symmetry that you've imposed on the scalar part of the model also holds for the Yukawas.
Just to clarify, when you're saying a fixed point here, you're saying I expect that there are other parameters that are running still.
Yeah, things run in general. I mean,
no, but you just
M11 squared, for instance, runs, and M22 squared runs, but the difference does not.
Yes, that's what I mean.
Yes,
okay, yes, that's fine.
Yes,
you mean so it's not really a fixed point. It's a fixed. In Wilson's terminology, there's a particular toning that you are flowing within that fixed point surface, or there's a fixed point surface, I suppose.
Yeah. So in any case, you include the gauge interactions, include the Yukawas, it's still 0. And it persists to all orders in perturbation. So now we come to the example that was appeared in this paper by these 4 authors that I've already referenced. And this was the parameter relation they had. This lambda1 equal lambda2, lambda6 equal minus lambda7, that's exactly the same as in GCP2. But what's different is instead of saying these things, m11 squared equals m22 squared, m12 squared equals 0, they threw those away and instead said M11 squared equals minus M22 squared. And then they did the calculation. And this seemed to be renormalization group stable. It was stable at one loop. They did 2 loops, it was stable. When they went even beyond 2, they actually proved it was stable to all orders in perturbation theory and in the scalar self-couplings, in the gauge couplings. For the fermions, they never got past 2 loops, but in any case, that was the result. And the question is, where did this come from, this relation? Now, first of all, the fact that lambda1 equals lambda2 and lambda6 equals minus lambda7, that's renormalization group stable, because if I go to this, I can view this as a softly broken GCP2 symmetry, because the only thing that's breaking the GCP2 is this relation here. And so you would expect these last 2 equations to hold. But it's this equation that's very puzzling. And so the first thing you might say is, okay, this is a weird relation, but maybe there's a basis transformation I can do. They'll turn it into one of those 6 that I showed. Well, there is no basis transformation at all that does it. So the next question is there a symmetry in the 2 HDM that's been completely overlooked after all these classification papers? And so the 4 authors decided to colloquially refer to this as a goofy symmetry, but they had to put Pedro's name at the end to make the acronym work. And so this is what they said. Okay, let's consider the following scalar field transformations. They proposed this as part of the symmetry. Now, I saw this and I said, give me a break. Phi 1 star does not transform into the complex conjugate of the transformed phi 1. What the hell are they doing here? By the way, this would be equivalent to saying that these bilinear phi 1 dagger phi 1 go into the negative of phi 2 dagger phi 2 and vice versa. Whereas phi 1 dagger phi 2 and phi 2 dagger phi 1 are invariant based on, you just stick that in. And indeed, if you impose this on the potential, you do get this relation. And so that was the first step of their proposal. But it gets worse. Because unfortunately, when you do this, it flips the sign of the kinetic energy term. So then they got even more strange. They said, what we're going to do is we're going to also transform the coordinate by an I, thereby changing the sign of, the covariant derivative by an I, and therefore that will reflip the sign back. And so the combination of these 2 symmetries is what they proposed is the symmetry explanation for this renormalization group stability. I did not buy this. This was in a talk that I saw they gave at a conference, and I sat there and I said, this can't be right. So it looked like to me that there was no valid symmetry explanation for the RG stable parameter relation. So that's the mystery that I attempted to address. Now, the 2x double model is a complicated model, lots of parameters. And so in order to make things tractable, I wanted to take the simplest possible version I could imagine where the same thing happens. And it turns out that all you need to do is look at the following toy model with one complex scalar field. Now, for the rest of the talk, no more gauge bosons, no more fermions. We'll just look at, this is an interesting problem of a scalar quantum field theory. So here's my theory of one complex scalar field, and this is the Lagrangian. Now I've imposed a discrete symmetry to get rid of linear and cubic terms. Nothing wrong with that. But now I'm going to impose the following very simple parameter relations. That this lambda 3 and this m1 squared are 0. And can work out the beta functions. And amazingly, they're 0. It looks like, and two loops, they're 0. So again, we seem to have a similar situation that we have a parameter relation, it's RG stable, and looks stable to all the distant perturbation. So
Sorry, but it was it as U2 symmetry. Didn't you do some generality?
yes,
There's nothing wrong with that.
He wants to lose it.
no, I mean this parameter relation has nothing to do with that.
Your Lagrangian, I would really like to see it in real variables.
We're getting there.
Okay, all right.
We'll get there in a minute.
Yes.
All right, now I can understand why lambda 3 equals 0 is a symmetry, because here's a symmetry transformation. If you impose that on this theory, it actually says lambda 3 equal to 0 and m2 squared equals 0, not m1 squared. So that means that this symmetry transformation is softly broken by the fact that m2 squared is not 0. But that means that lambda 3 equals 0 is RG stable. So we understand that. But again, why is m1 squared equals 0 RG stable? There doesn't appear to be any symmetry, legitimate symmetry. So here's the goofy-like symmetry in this case. Phi goes to phi, and phi star goes to minus phi star. Again, equally abhorrent to what was done in the 2HDM example. So if you impose this symmetry, you get m1 squared equals lambda 3 equals 0. Now, of course, when you do this, that flips the sign of the kinetic energy term, and then we have the same story again. So I conclude this is sort of a toy model of what they were seeing in the 2's double model. Okay, so you wanted to see the real version? Here we go. So I give a word to this, and you'll see a little later in the talk why I'm using this vocabulary. I call this realification of a complex scalar field theory. All that means is you take the complex field and you write it as phi 1 plus I phi 2 over root 2. The realification of a complex scalar field theory does not change any of the physics. It's just expressing it in different variables. All right, so here's the potential. And now we can translate our parameter relations we had before. And look at this. This looks almost exactly like the ones were in the 2HDM. Then m22 squared was minus m11 squared. And then there was sort of the two other coupling relations that look like that. The notation here is in this footnote. It's sort of the obvious notation. Tells you what scalar fields appear multiplied by that coefficient. So as I said, these three parameter relations are equivalent to m1 squared equals lambda 3 equals 0 previously. And so now, let's look at this particular symmetry transformation. Phi 1 goes to phi 2 goes to minus phi 1. What that would do is that would set m11 squared equals m22 squared, m12 squared equals 0, and then these two things. So this RG stability of these coupling relations are again due to the softly broken symmetry. But we don't, again, have symmetry explanation for m11 squared equals minus m22 squared. So what would be the goofy symmetry transformation here that would yield this particular parameter relation? Well, here it is. Phi1 goes to I phi2, phi2 goes to minus I phi1. You stick that in, out comes these parameter relations. But in the context of the real field theory, this is completely illegitimate because I'm not allowed to use complex numbers, and it's a real field theory. So this is how it shows up here. And again, of course, as noted in this footnote, this thing would change the sign of the kinetic energy term. But nevertheless, these, how did I write this? Oh, yes. M11 squared plus M22 squared, the beta function of that at the symmetry point is 0 to all orders in perturbation theory. Now, I'll just flash this up briefly. For an arbitrary scale of field theory, the one-loop beta functions are known, the two-loop beta functions are known. Actually, the three-loop beta functions are known as well. We did all of our calculations through two loops, but hopefully you'll see by the end that it's we could do three loops, but it doesn't even matter. You'll understand when I get there. What's kind of interesting, if you look at the two-loop beta functions, there are different structures here. This is kind of independent to that. This is kind of independent to that. What that means is that if you have beta functions that vanish, not only does the full beta function vanish, but each particular term, not term here and here, but this together is one thing. This is one thing. This will vanish. That will vanish. So the beta function relations you get are even stronger than just saying that the overall beta function vanishes, and this will become relevant later. Okay, so here was my proposal to understand where this strange behavior of RG stability was coming from. And it involves something which I call complexification. And the hint to this was the illegitimate symmetry that I wrote before would be legitimate had these real scalar fields been complex scalar fields. And so what I proposed was to complexify the theory, which now is actually changing. The number of degrees of freedom is being doubled. And so the proposal is to promote the two real fields, phi1 and phi2, to complex fields, and now impose this as a legitimate symmetry. And then also I will impose this symmetry that enforces reality conditions on all the parameters in the model. And now the resulting parameter relations of the complexified theory are RG stable due to symmetries. And so what I hoped to be able to show was that the RG stability of the parameter relations in the complexified model would somehow guarantee the RG stability in the original model, even though the symmetry was no longer there. That was the strategy, but I had to show that it actually works. It's not automatic. So the complexification recipe: promote the real scalar fields to complex scalar fields. The complexified model is defined to employ canonically normalized kinetic energy terms. So I just add this as a kinetic energy term. I don't try to say this comes from the other place. This is just the recipe. I'm still getting rid of odd numbers of fields. That's just for convenience. Then I promote the goofy-like symmetries to legitimate symmetries of the complexified theory. And I do impose CP symmetry so that all the scale potential parameters of the complexified theory are real. And now, it turns out that to make this whole program work, it all was a question of inventing a notation that would basically do all the work for you. And it's really amazing because once you see what this notation is, it almost falls out. And so let me explain the notation I have used. So now when I have field phi A, its complex conjugate, I'm going to give it a label A bar. So for instance, a basis transformation would look like this. And A, B, and C run over 1, 2, A bar, B bar, and C bar run over 1, 2. And the rule that I give is I sum over unbarred, barred index pairs. That's the rule. Now, by the way, in the literature of lots of papers, the notation that is more traditional is that the barred indices just appear as upper indices. The unbarred indices appear as lower indices. Then you have to remember that an upper index is implicitly complex conjugate. And you could do that. I just found it a little easier to follow things by writing it this way. But if
Why did you find it easier?
why?
The way his brain works?
It's just the way my brain works. I have written like the book I wrote with my two co-authors, From Spinners to Supersymmetry. We used the other way of doing it. And then conditions for hermeticity and all sorts of other things. You have to place the indices in precisely the right way. And I would always stare at it, and I was never quite sure whether I got it right, but often I did. Here, I don't know, I just found it a little bit more straightforward. But you could be the judge of it. Okay. So here's the scalar potential of the complexified model according to the recipe. Now there is the one disadvantage of this barred unbarred notation is if the resolution of your screen is not sufficient, you're not going to be able to notice the difference between a barred and unbarred index. And you'll notice that I have two different types of mass terms. This one has one unbarred, one barred. This one has two barred, and they're different. And I use the same symbol m squared, but you just have to follow things. You have to pay attention to the index structure and be able to see clearly all the bars. But if you're, all right, maybe on a screen like this, it's getting a little hazy, but on my Mac, which has a very sharp screen, it doesn't seem to be a problem. Yeah.
But if you're sitting here, you can see it fine.
Oh, okay.
Just the first term in the potential, it looks like it has only unbarred indices like that. So
Sorry?
In the first index.
It's an A B bar.
Yeah, this B bar is summed with that B.
Yeah, the first one, but the third one.
Or the third term.
Oh, I left out the bars. Oh, how about that? Oh my God. Oh, that's not.
It could be the projector that's stopping it.
No, I don't think so. I'll go back and fix that. Thank you. Yes, that should obviously be two bars. I threw the stars in. The stars are sort of extraneous in some sense, but it's okay.
Because it's an extra hint, but.
Yes, an extra hint, right? Okay.
What is the start number on that one? I'm gonna look it up.
That's okay. I'll remember. Okay, so here's the potential. Then you impose hermeticity and permutation. So for instance, this one, A, B, C, D, this lambda A, B, C, D has to be totally symmetric under the interchange of everything. So you get various conditions. And so then you find that some of these parameters are real and then the rest are complex. But then, even though they're complex, we're going to impose a CP symmetry, so they're all going to become real at the end. But I want to keep track of the index structure as we go along. Okay, so now we impose that goofy symmetry, which is no longer goofy. It's a legitimate symmetry, and that imposes the following relations on the parameters. So I've written that out here. So these are relations with 4 unbarred parameters. These are relations with 3 unbarred and 1 barred parameter. These are relations with 2 unbarred and 2 barred parameters. And of course, there are 2 other cases, like 4 barred parameters, but they're just the complex conjugates of these. So once I know this, I know everything. Okay.
Sorry, how many parameters did you end up with again?
There it is. So it turns out that there are 11 parameters, 11 quartic parameters, and after you impose a symmetry. Actually, sorry, not after you impose. After you, yeah, I think after I impose a symmetry. Yeah. So there are 3 squared mass parameters and 11 quartic parameters, and these are where they come from. So one of the things you see is that this guy, which has no bars or 4 bars, because everything's real, is just these 3 parameters by themselves. There's no mixing. So these are really independent tensors, and that's going to be important as we go along.
And before you impose the symmetry, how many parameters did you have?
I go look in the paper. I wrote about 35 or something. I forget them. But it's in the paper we do the counting. Okay, let me just say one word about this language of realification and complexification. And what inspired me is Lie algebra theory. Of course, these are concepts that actually, you don't need the algebras. All you really need is a vector space. But for Lie algebras, they play a particularly important role. And there's a very nice analogy. So we started out with theory of one complex scalar. We realified it, which doesn't change it, but just changes how you express it. And now you've got 2 real scalars. Then we complexified and got a truly new thing. In Lie algebras, here's a standard example everyone knows. SL2C, which is the Lie algebra, is the set of complex traceless 2x2 matrices. When you realify it, you get something which is called SL2C with an R in front of it. And this is completely hidden from view in most textbooks. And therefore, when I teach students this, they get very confused. First of all, they don't really understand the difference between real and complex Lie algebras to start off with. But then again, you know, this is this famous relation relating this to the Lorentz group. The Lorentz Lie algebra is a real Lie algebra, so you can't. The books that say this is equal to that is already confusing. And so what they've really done is they've realified it. And if you want to understand the mathematics, SL2C is the complex linear combination of those 3 generators. And what you do to get SL2CR is you take real linear combinations of these 6 generators, which is basically these 3 generators and then I times it again. But that's really algebra is always a real linear combination of basis vectors. So.
But this is, I mean, SU2 is not the same as SL3. It's not the same relation. The 2 component representation of SU2.
Well, yeah, that's a slightly different story. Yeah.
I mean, SL2C appears there, the bias spinors of SL2C.
Well,
that's the 2-dimensional complex representation, right?
Yeah, but I'm not talking about representation. I'm talking about the actual structure of the groups, the algebras. But in any case, when I complexify this, what that means is I want to take complex linear combinations, not real linear combinations. And so when you complexify this, you get 2 copies of SL2C, which, by the way, is isomorphic to SO4C, which is just the complexification of that guy.
It's a statement about the coefficients of the generator.
Yeah. So in any case, I like this analogy because it really gives you the essence of what we're doing here. We're creating new sets. Okay, so now I've got my complexified theory. Now I want to compute the beta functions, and well, I'll check that they're 0, but at the symmetry point. But I know the symmetry guarantees that this is going to be true. Now, one way of calculating the beta functions is to use those formulae I had earlier on. Those formulae were for the real scalar field theories. So in order to use those formulae, you would have to now realify this complexified model, like so. Now I have a model of 4 real scalars, write everything out, and then write the beta functions. But we wanted to write the beta functions directly in terms of the complexified parameters. So it took a while to do that, but here are the expressions that you get. And the amazing thing, if you study this, you realize that everything, again, this is why the notation is so powerful. In some sense, it's the covariance of the expressions that tell you what the form of these equations are. The left-hand side has 2 barred indices. That means the right-hand side has to have 2 barred indices when you sum over everything else. And there are only 3 different ways to write it in this case. And so the only thing one would really need to calculate are the coefficients. We did calculate the coefficients, but it turns out we don't even need to calculate the coefficients. But remember, I told you that things with different index structures are independent tensors. And so if the left-hand side vanishes, each separate term separately vanishes on the right-hand side at the symmetry point. So in fact, we didn't even need these coefficients, but we got them anyway. So given a symmetry that imposes this relation in the complexified theory, m11 squared equals minus m22 squared, we can rewrite this in this way, a parameter relation like this. Here are the C's that do it. And the symmetry guarantees that this is equal to 0. So I take that beta function I had here, I multiply by CAB, where the C's are given like so. But again, each term separately is going to be 0. And so we actually get these 3 at one loop, these 3 results. And now here's the first hint that things are working out for us, because of those 3 terms, the second term looks exactly like the term you would have gotten in the original toy model of 2 real scalar fields. This is what you would have gotten there. And you compare that with that, and remember, this is A bar, B bar, C bar, D bar, but I've imposed reality conditions on the coefficients. So this is the same as lambda A, B, C, D. And so this looks exactly the same as that. And so this shows you that at least one loop, it's the one loop stability is a consequence of the symmetry of the complexified theory. So then we went to 2 loops to see, does the same thing happen? So at 2 loops, this is the result in the real theory. And remember, I told you there were 2 separate terms, and each one had to be 0, so here they are. And so now what I want to do is write the corresponding terms in the complexified theory. So what I would, in principle, do is want to derive the beta functions in this notation, the 2 loop terms. But I've already told you that I don't even really need the coefficients. All I have to do is work out what the possible tensor structures are. And each one of them is separately going to be 0. And so that's what we did. And so here it is. This was the unique set of 2 results that you get. So this is just one of the terms. These are just some of the terms appearing in this with some coefficients, which, as you can tell, I don't care about anymore. And these have to both be 0. So now if I compare this, and on the next slide, I'm going to compare it with the real the equations from the real scalar field theory. They're going to look kind of like this. Now, if you look at this, this has 4 unbarred, 4 barred, but the 4 barred is equal to the unbarred. Same here. I have barred on the M squareds, but that's the same as the unbarred. The only problem here is that this guy here, to make the indices match, you have to have one term with 2 barred and 2 unbarred. So it looks like it's not going to quite work out. However, a remarkable thing happens here. First of all, the sim means I have to impose these parameter relations. Here are the parameter relations. And if you compare the parameter relations of the unbarred, of the no bars and the 2 bar results, they look almost the same. There are some stars involved, but again, you can ignore the stars because everything's real. So these are compatible parameter relations, with one exception, that they're the lambdas with no bars or 4 bars is completely symmetric. The one with 2 bars and 2 bars and 2 no bars is not completely symmetric. So there's in fact one more degree of freedom compared to this. But here's the final point, which makes this all work. And it's really amazing. If you look at this equation here, for instance, this one, this has to be true. Remember, the lambdas with 4 bars and the lambdas with 2 bars are completely independent. Remember when I wrote the 11 parameters, they involve different guys. So this has to be true, this equation, for any numerical choice of lambda with 2 bars and 2 no bars. And if it's true for any choice, it's certainly true if I numerically set this equal to that. And that was the final step that needed to be done to make this all work. Because once you do that, these equations are algebraically identical to the beta functions in the real scalar field.
So I just wondering about the logic. So I understood the logic of what you said there.
Yeah.
You could set those 2 guys equal.
Yes.
Then you get the original real theory.
Right.
So that reverses this. I mean, you have to do that now.
Well, in order to, I want to show that the beta functions in the real theory are, I want to understand why they're equal to 0. So this is more general than that.
Yeah.
So it's true even if this guy were not equal to this guy.
It's not trying to get at what happens. It's that.
Well, if they're not equal to that's okay. But if they're not equal, then this equation is not matching the other one.
Yeah,
It's just a more general theory.
It's just more general.
okay. Yeah.
I am allowed to make this choice because this is true, because these are completely independent. That was the thing. And it really shocked me in some way. I had to actually work out all this and prove to myself that it really didn't matter what the value of that was. But it really was. It's because of the independent nature of the various structures. It was just very powerful. And the amazing thing is, so now go to 3 loops. So what makes this work when you go to arbitrary loops? What makes it work is that when you work out things like this, I've just written things with this particular structure. There are other structures. The beta function is the sum of this, and a whole bunch of other things with different structures. Some of them involve 3 bars and 1 unbar and stuff like that. But all I have to do is find one particular structure in here which involves just an even number of bars or unbars. So because what I've shown you that if I just have all bars or all unbars, they're the same. And if I have 2 bars and 2 unbars, I can just set it equal. So as long as I have a term like that, and there will be one term like that, which will look exactly like the beta function in the real scalar field theory at that loop order. There'll be lots of other terms, and they're also all zero, but I don't need them. All I need is the one that looks like that. And so this argument extends to all orders in perturbation theory. And so just kind of to summarize, schematically, what I've written is the beta function of this form here. Now, in this beta function, at any order in perturbation theory, it contains exactly one factor of m squared and then n factors of lambda at order n. And then I just have to tie the indices R, the various indices, in a way such that this whole thing has an index structure A bar B bar. And when you do that, each term separately is going to be zero. So every term fk for any value of k is going to be zero. And then, as I said, there'll be always at least one value of k where this just depends on tensors with an even number of unbarred and barred indices. And so that gets you the result that matches the real scalar field theory. And so bottom line is the RG stability, the parameter relations of the original real scalar field theory is inherited from the symmetry of the corresponding complexified theory. Okay, so I just have one or two more items to mention, and then we're done. Future directions. So the recipe to create a real scalar field theory with an RG stable parameter relation in that sense of the symmetry is start out with a theory of n complex scalars, which has some parameter relation, impose CP to get reality of the scalar potential. Take that theory and restrict it to the holomorphic terms. So in the example I have here, what holomorphicity means is it just depends on the scalar fields and not their complex conjugates. So I take the Lagrangian, I restrict it to that, and now I reinterpret that as some real scalar field theory. So now I'm sort of going backwards.
HF means?
HF means Higgs flavor symmetry. That's just a UN. If we have n scalar fields, UN, n complex scalar fields, a UN. It's the symmetry group of the kinetic energy terms. So then I construct. So now I'm going backwards. I construct the theory of n real scalar fields, replace phi A with a real field, and then I replace the kinetic energy term with canonically normalized term for the real scalar field theory. That has a symmetry group ON, whereas the original one had UN. If the Higgs family symmetry of the complex theory can't be embedded in ON, then the Higgs flavor symmetry of the complex model will not survive when we get down to the real model. That's really what happened in the toy example I gave you, because if you remember the symmetry in the complex for the complexified theory had eyes in it. So the matrix in some sense was 0 minus I 0. That can't be embedded in a O2 subgroup when we go back to the real theory. So that's kind of why the symmetry was not present, the legitimate symmetry wasn't present in the original model. And so this would be sort of a recipe to create new examples of this phenomenon. And then the next step would be to apply the results of this talk to the goofy symmetries of the 2HDM. So now I'm 100% sure that this technique would work for the 2HDM as well, but one should go through the exercise. So in the 2HDM, one would first realify the model. And now the goofy symmetries take this form in the realified version of the 2HDM. Notice they have eyes in it, so this is not a legitimate symmetry, but now I complexify. Now it's So then I would then have a complexified version, and then the whole story would go through. Then I would be able to verify that this set of parameter relations that the goofy paper found could be explained by the symmetries of the complexified theory. Now, to do this in full detail, you would require to extend our techniques to include the gauge and Yukawa sectors. In other words, compute the gauge contributions to the renormalization group equations. I'm pretty sure that would be incredibly straightforward. It would work the same way. The Yukawa sector, the authors of the goofy paper never proved an all orders result for the Yukawa contributions to the beta function. So one would have to think a little bit to make sure that the complexification story would work. Because if it works and you can identify the symmetry and extend it to the Yukawa sector, then you're guaranteed that it worked to all orders perturbation theory. And the last comment, the question that I've been asked before is there some more sophisticated idea that explains why one had to go through all this? Here are some buzzwords that have been thrown out at me. In about a week or so, there will be a paper posted on the archives, which I think attempts to use concepts of outer automorphism, so a different type of explanation to explain where this comes from. When I was at the KITP in January and discussed this with people, I was asked, well, are there some generalized symmetries which are not sort of standard symmetries in the original theory, but maybe there's some new structure that we don't quite understand that can be invoked where you don't have to go and do the complexification? It would be interesting to see if something like that exists, but so far there have been no concrete proposals. So I guess I'm out of time, and so I thank you for your attention. Yeah.
Could you show us the two real scalar quadratic identities in the toy model?
The original toy model. Sorry.
You had it yeah.
That one?
That potential doesn't look unbounded below. It looks unbounded below. Phi 2 squared is greater than phi 1 squared.
You're asking about unboundedness from below conditions.
Potential to state. No problem, even if it isn't, it's no problem for perturbation theory.
Yeah.
What do you think, Brian? It is.
The potential is unbounded below.
Yeah, no, I mean, it doesn't rule
I'm
out
just
the
wondering-
RG equation. So.
No, the perturbation theory is fine.
Yeah.
I'm just wondering, would this be genetic feature of complexification?
That's a.
Because what you could do there.
Well, I mean, if what you're saying, I have to think about it, but the same thing would then have to be true for that 2HDM model.
Well, I don't know, just that potentially.
But this is
If you do
basically.
If you do your goofy symmetry.
No, before the symmetries, I mean.
Yeah, the potential can be either side.
Sorry?
The potential can be either side. Then that potentially looks to me look can be either positive or negative.
How do you see that, Ryan? Which one are you?
Phi 2 squared is larger than phi 1 squared. And lambda 1, 1, 2 is positive.
1, 1, 2 is positive.
It's you take magnitude of the phi.
There's a phi 1 to the fourth and a phi 2 to the fourth terms, which should say.
Yeah, but they're both fourth order phi.
I mean,
they phi 2 to be phi 1.
Don't you think there are parameter regimes where this is not unbounded?
It looks to me as though it's unstable, but maybe I'm.
What happened if, I mean, there are certain quartic terms.
Take phi 1 and phi 2 to the same order of magnitude, both positive. Phi 2 is slightly larger than phi 1. Then the last term is negative.
The last term is negative, but then this thing compensates.
But that depends on the magnitude of the lambda.
It does. But what I'm willing to bet you is there are regions of the parameter space where this is
Oh,
perfectly
that's possible.
compatible.
You know, the point
Yeah.
I'm trying to make was that for general parameters, that can be out of sight.
Yeah. I mean,
So,
when you do any, like in the 2HDM, when people do phenomenology of models, that's the first thing they check. They check what's the parameter regimes where
Stable.
but if you take a general set of parameters, you do your goofy symmetry.
Yeah.
You change the sign of kinetic time.
Yes.
Change the sign of Lagrangian. So the kinetic time is then positive, your potential can still be out of sight.
True.
Would this be a general feature of complexification that you end up with potentials that are not going to be low?
Well, I mean, you can have potentials unbounded from below where you have completely legitimate.
Oh, I understand that. Yeah,
So-
no, I'm just thinking it's maybe some feature of this symmetry that this complexification means that you inevitably end up with a parameter regime with the potential to be unbounded below.
Well, I mean, even in the 2x double model, without any goofy symmetries, there are definitely regions where it's not unbounded, where it's unstable. So I think it's more general.
I think what you're doing is you're imposing a complex structure on the space of couplings.
Mhm.
And you're restricting two couplings that respect some holomorphic symmetry. I mean, the RG flow seems to respect that complex structure.
Yes. Right.
And that's what you really observe.
Yeah.
If you be able to get the theory set up with that complex structure, then it will be respected by RG flow.
Right. Mhm.
The question then is whether that's a deeper symmetry, whether that imposes a deeper symmetry.
Yeah.
It could do. It could do because there may be a rotation in the space of fields, which is similar to what they're doing there.
Mhm. Now, I know the paper that's going to come out in a couple of weeks, they have some other way of getting the sign back to its original, the kinetic energy term back to its original form. But I haven't studied the paper yet. I got an advanced copy just yesterday, but I haven't looked at it. So I'll be interested to see whether there's any relation with the ideas of that paper. But
I'm wondering, are you going to run into some problems with the Yukawas?
yeah, that's an open question. That's on the menu.
Because the Fermions don't quite respect the same.
Yes, but the only thing I know is that at least in
No,
but the authors
they found it, so it suggested it would.
they at least at two loops it was fine, but they weren't able to generalize beyond two loops at least.
Probably is fine.
The goofy symmetry, ignoring the kinetic terms, it never violates CP, right?
So what was the question exactly?
Yeah,
The goofy symmetry.
It is ignored in CP.
And the goofy, what they call the goofy symmetry, it's a CP, it doesn't violate CP. I mean, CP.
CP is a separate.
Yes.
It's a separate issue.
I know. What I want to ask is that when you realify your setup and impose the goofy symmetry and then complexify, why do you need to impose CP again? Because we never broke CP in the first place. Why
No, because in the complexified theory, if I don't impose CP, then I have complex parameters. It's a little bit more complicated to match with the beta function expressions that I have in the complexified theory with the original real scalar field theory. So it's much more straightforward, and I don't lose anything by imposing CP.
But also the physics of the complexified model is completely different. Anyway, so
Yeah.
we shouldn't take it too seriously, because that's not the one you're interested in.
Right.
And you definitely wouldn't call it a custodial symmetry.
Sorry?
You definitely wouldn't call it a custodial symmetry.
No. Well, and there's no custodial in the pure scalar field theory. That's not even an issue. Yeah.
So when you complexify the theory, is it obvious that you only uncover one extra symmetry, or is it possible there are others that can?
Sorry,
Is it obvious that you only uncover one of these goofy symmetries, or is it possible that there is other that you haven't seen yet?
others,
I mean, obviously the complexified theory will have bigger symmetry space, so are there
Yes.
some others that you can
Um,
somehow make sense of?
yeah, I mean, it is true that when I complexify the symmetry, the real theory, the question is, which real theory am I complexifying? The original one before the goofy symmetry or after? And so since I had a very specific goal in mind, I wanted to make sure that the symmetries were sort of complexified as well. So, but yeah, I mean, you're definitely right that there are other symmetries you could impose on the complexified theory, which may or may not have any implications for the original real theory.
You see, because in principle it sounds like, you know, this can uncover, for example, for the double Higgs model, it can uncover a lot of symmetries on top of the extra of these things that are known to be the basis.
Well, I think my conclusion is that the original 2HDM classification of symmetries is still valid.
Okay.
That hasn't changed.
Yeah, but there is one on top of that, at least one of the symmetries. So.
Right. I mean, that doesn't mean that there are a bunch of other parameter relations of the 2HDM beyond those classified symmetries that sort of have a similar property. So far, only one's been discovered, but in fact, the paper that will come out in a couple of weeks, I think, makes the claim of being able to find a whole slew of extra parameter relations that have sort of similar properties, at least in the 2HDM context.
Okay.
And these are all parameters, I'm assuming, softly broken. Quadratic parameters, right?
Well, yeah, I mean, the parameter relations that are not being explained by symmetries, my impression is that it's only relevant for the dimensionful parameters. That I haven't seen yet any relations of coupling constants that had a similar effect, that you couldn't even find the symmetry in the real theory that would explain that particular relation. Although I should say that if you do find one of those, I think the complexification program would still work to explain those. And in fact, we did that little exercise to explain to explain these beta function relations from the complexified theory point of view by the matching. You can do that, but it's not necessary, because already in the real scalar field theory, it's the result of a softly broken symmetry. So
I'm wondering, can just your complexified, your realified complexified theory, if I look at that and the action for it,
yeah,
it looks natural to look for instanton type solutions.
okay,
With just those general parameters.
yeah,
And I'm thinking that you might get non-perturbative information from that.
that's an
Along the lines of Lipitov, you remember, that old work.
yeah, that's certainly an interesting proposal.
It seems like a very natural thing to do now.
Uh-huh.
Now that one sees it.
Right, yeah. Good. Okay, well, I thank everyone for your attention.
That was very stimulating.
Thank you.
That was very nice.
Thanks.